gonna share my screen and we'll get started.
Great, thank you.
All right, so it says here in the instructions, find the first six terms and then the 100th term of the explicitly defined sequence. So the first term is when n equals 1, and this is u sub 1. You're putting 1 in for n, so it's 1 plus 1 over 1. You're just putting 1 in wherever you see an n, and that is 2. N equals 2, that's u sub 2. 2 plus 1 over 2, that equals 3 halves. N equals 3, u sub 3 equals 3 plus 1 over 3, which is 3/4. I'm sorry, 4/3. Put the wrong thing. And then n equals 4, u sub 4 equals 4 plus 1 over 4, which is 5 over 4. So you're starting to see the pattern now. So at some point you may not even need to write all this. You can just say, okay, it's 2 3/2, 4/3, 5/4, comma 6/5, comma 7/6. And that's the first 6 terms.
Okay, that makes sense.
And then it says it wants you to find the 100th term, so you just have to put 100 in. It's 101 over 100 for that.
Okay, awesome.
So sometimes you see the pattern, but if they get more difficult, like in number 4, the pattern may not be as clear, so you just have to work it out, and it's just more effort. Now, does your instructor generally allow you to use a calculator on the tests, on the homeworks?
She has different sections on the test, but this would probably be a
That's
no
right.
problem.
Okay, because there's ways to do this on your calculator where it just generates the first 6 terms, and it's obviously really nice because you don't have to do all these calculations. But so D1 is the first term. That's 1 squared minus 5 times 1. Okay, so this one illustrates that it could be negative. 1 minus 5 is negative 4. N equals 2. D sub 2 is 2 squared minus 5 times 2. So that's 4 minus 10, which is negative 6. N equals 3. D sub 3. 3 squared minus 5 times 3. That's 9 minus 15. That is also negative 6. N equals 4. D4 equals 4 squared minus 5 times 4. That's 16 minus 20, which is minus 4. N equals 5. D sub 5 equals 5 squared minus 5 times 5. That's 25 minus 25, which equals 0. And then the next term, n equals 6. D sub 6 is 6 squared minus 5 times 6. 36 minus 30, which equals 6 there. And then when n equals 100, D sub 100 equals 100 squared minus 5 times 100. Definitely probably go to a calculator on that. 100 squared is 10,000. 10,000 minus 500 is 9,500. This one does not have a pattern. I mean, it kind of did, but because it's squared, it's following the shape of a parabola, so you don't. It's not gonna just increase the same amount each time.
Okay. So what would be like the limit on this one?
None. There's no limit. Like, it goes on forever.
Okay.
And that's the point of these things. They go on. They're forever. They start at 1 and they go to infinity, generally.
Okay, awesome. Thank you.
Okay. There's a lot more to say on these, but I'll just focus in on what the actual assignment is asking you to do. But I can give more guidance if needed. So let me snip in the next question, number 7. And the instructions here, they say, find the first 4 terms and the 8th term of the recursively defined sequence. So the word recursive here, it means that the next relies on the previous. Okay, so I'll try to explain that here. B1 equals 2, and that's for k equals 1. That's just given. You don't have to do anything for that. That's given. When k equals 2, okay, we're putting 2 into this, actually, okay, so, all right, this is like k equals 0. It's a little bit backed up here. When k is 1, when you put 1 in for k here, you get b sub 2 equals, because that's 1 plus 1, equals 3b sub 1. Okay, so I just put k equals 1 in here and here and here. And then you have b sub 1. B sub 1 is 2, so this is 3 times 2, which is 6. So your b sub 2 is 6. So now when k equals 2, you're putting 2 into this formula. You get b sub 3 equals, and you're putting 2 in there, 3 times b sub 2, which is 3 times 6, which is 18. Now, if k is equal to 3, you're putting 3 into this formula up here. It's b sub 4 equals 3 times b sub 3. In other words, and I'll just write in words, it's 3 times the previous term. So 6 is 3 times 2. 18 is 3 times 6. B sub 4 is going to be 3 times 18, which is 54. That's b sub 4. So b sub 5, the fifth term, is going to be 3 times this. Sometimes you can see these patterns emerge, and you definitely want to use them if you can. This is a 486. If this wasn't clear, I think we get another shot at going through it, but let me know if you'd like anything clarified on this.
Yeah, that makes sense. How would
Okay.
you, if they like ask you to find like, oh, what's the 60th term?
Yeah, well, they kind of do that here. So this is, they're asking for the 8th term. Well, to do the 8th term, it's 3 times the 7th term, which means you need the 7th term. So you can't like get around it. You have to find it. So in your question, I think you said 60th, you'd need the 59th term when it's recursive.
Right.
When it's recursive. When it's not recursive, you can just find it. So B7 is going to be 3 times 486. And that's 14. That's, what is it? 58. Might check that. And then B8 is 3 times 14, 58. You have that number handy?
Yeah, it's 4,374.
Okay. So you just have to keep going. You can't, there's no shortcuts to getting that,
Okay.
that one. All right, up to number 10. Number 10 is a recursive sequence where the recursive sequence can rely on more than just the previous term. It can rely on more than one previous term. So when k, they tell you it's C1 equals -2 and C2 equals 3. So now when k equals 3, you're putting 3 in for this k. So C3 equals C3 minus 2 plus C3 minus 1. And you'll see that reduces to C1 plus C2. So C3 is equal to whatever the C1 is, which is -2, plus whatever C2 is, which is 3, and it equals 1.
Okay.
So now C4, that's when k equals 4, that's equal to C4 minus 2 plus C4 minus 1. And that's C2 plus C3. So at some point you might realize in words it's it's adding the previous two. And sometimes it's easier to like see it in words than to like keep writing these underscores. So the previous two, it's 3 and 1. It's 3 plus 1, which is 4. So C5 is C4 plus, I'm sorry, C3 plus C4, which is Where's C4? C3, C1 plus 4, which is 5. You're just adding the previous two terms. C6 is C4 plus C5. It's adding the previous two terms, 4 plus 5. So that's why sometimes it's better to write these out sort of in like -2, 3. And then the pattern is, oh, I add those. So that's 1. Then I add those. That's 4. Then I add those. That's 5. Then I add those. That's 9.
Okay, yeah.
So to
That,
get the 8th, well, we got to find the 7th. You got to add those, which is 14, and then add those, which is 23.
when you have like a recursively defined sequence, is there any way to like make it into an explicitly defined sequence, or does it just have to stay like recursively defined?
You can, yes, but there's maybe you've heard this in other classes. There's this principle of linear, the linear position super principle or principle of linear position. Essentially, it's like if you have two linear functions and you combine them, you get another linear function, and that's what is required to get it.
Oh, wow. Okay.
Yeah. So like 5 and 6 end up being you can create a explicit sequence. Now what you do, maybe you're thinking of this because your instructor asks questions. What you do is you still write out a bunch of terms, then you find the formula for that. There's not a good way to like come up with it without writing out a few terms.
Okay, so you can't get it like directly from the recursive sequence. You have to
No.
find.
Well, you could, like, that's a really advanced thing. I mean, it's something like I mean, I'm sure someone has done that, but it's beyond the scope of your class. Maybe,
Okay.
but I mean, I don't know what your instructor emphasizes, so I could be completely wrong on that. So, like in real life, we build systems that have inputs to them. Like think of a car, and they have outputs. Okay, something in your car has an input. Like you turn a knob on your AC and outputs cold air, right?
Right.
Well, your output sometimes feeds the input. Like it's too cold or it's too warm. So this feedback is essentially you can think of this like a recursive sequence where you take some information here, you feed it back in to get a new as an input to get a new output.
Ah, okay.
Okay. Now I doubt that's ever explained this way, but this is what happens in real systems. But you never get any context. You're just dealing with numbers.
Right.
But almost everything, and you do this yourself. You do something. You decide, okay, did it work? I don't. Maybe whatever. Cooking food. Oh, it's too too much salt, not enough salt, not enough sugar, whatever. And you constantly are iterating. It's called an iterative process where you continuously refine what you're doing. All right.
Wow.
So number 13, it says determine whether the sequence converges or diverges. So this is very challenging for most students because it converges, meaning it might approach some number, and you might not believe it or not. So this one converges to 0.
Yeah, that makes sense to me. I get
Okay. So we're going to just briefly say like 1 over a large number is 0. 1 over a small number is infinity. And that's about as far as we can go in this class. So the second one I'm not seeing, but you can say that. So now 16 is slightly different, but what you have several options here to try to figure this out. Like you can just write out a few terms to see if you can figure it out. You can also graph this. That's probably what I would suggest doing if you are comfortable graphing, or if you at least remember how to find horizontal asymptotes. You remember that from when you were studying rational functions?
Oh, it has left the brain. Actually, can you refresh me on how to find the
Sure,
horizontal
sure. So
asymptote?
we're just going to write this f of x equals 2x minus 1 over x plus 1. This one has a vertical asymptote where x plus 1 equals 0, the bottom,
Mhm.
which isn't what I said, but that's part of this. And then it has a horizontal asymptote at y equals 2 over 1 because 2 and 1 are the leading coefficients and they have the same power. So the thing that this approaches is 2 because it has a horizontal asymptote at 2. Okay.
Can you say how you found the horizontal asymptote again?
Yeah, there's a it's based on the degree of the numerator and the denominator.
Mhm.
So let's look at something pretty straightforward. So 1 over x, this is like case 1. The degree of the numerator has degree 0 because there's an x to the 0, so it has degree 0. The denominator has degree 1 because it's x to the 1. When the denominator is greater than the numerator, this thing always goes to 0. So if you were to graph 1 over x, it looks like this and like this. So over here on the right, this approaches 0. Do you remember that?
Yeah.
Okay. So case two is when and I'll give you an example of this. It's like x plus 1 over x minus 1. Here the numerator has degree x to the 1. There's power of 1 there, so that's 1. It's the exponent. The denominator has degree x to the 1. There's a 1 there, which is 1. So when n equals d, the horizontal asymptote is where y equals, and it's a fraction. It's the ratio of the leading terms, 1 over 1. Ratio of
Mm,
leading terms.
that makes so much sense.
Okay, so now if we go back to our problem that we're looking at, the one that we care about here, you have to treat this like these are x's. So it's really 2 over 1, and it approaches 2.
Okay, but it'll never reach 2, right?
Well, it does at infinity.
Right? Okay.
That's what because somehow you were convinced that this reaches 0, and it's the same idea.
Okay.
Now,
That makes
now, now, if you want to take calculus, you'll have a little bit more explanation about how this is proven. I'm not sure how much your instructor will just, assume that you're okay doing, but um, yeah, I leave it at that. Let's go on to 19 and see what we can make of that.
okay.
All right, so this is a recursive sequence because the next term, which is an plus 1, relies on the previous term, which is an.
Okay.
Okay, so the first term is 1, and now when n equals 1, a sub 2, because 1 plus 1 is 2, equals a sub 1 plus 3. So this is a2 equals a1 plus 3. a1 is 1. 1 plus 3 is 4.
Okay.
Now when n is 2, it becomes a sub 2 plus 1 equals a sub 2 plus 3. A sub 3 equals a sub 2 plus 3. So we're starting to see a pattern. It's the previous number plus 3. So that's 4 plus 3, which is 7.
So this will like approach infinity, right? Because it's never going to get
It,
smaller.
it will approach infinity. Exactly. Now, you asked this question. So it's 1, 4, 7, 10, 13.
Oh, yeah, and you could define this by being like
You could do an explicit one. So the explicit one here, and this is a cheat on this, is you actually define this previous term here, which is minus 2, and your
um,
an equals minus 2 plus whatever the jump is, 3n, because you're adding 3 each time.
okay. That makes sense.
But it's not there. You can't do that. Your instructor probably won't like that, but that's the more efficient way to do it. So now this is a graph. This is like us saying y equals minus 2 plus 3x. Well, where does that go? It goes to infinity.
Right.
So it doesn't converge. You would want to say diverges. I bet your instructor's pretty particular about that.
Yeah. Okay, that makes sense.
All right. Moving on to 22. All right, so 22 has a bunch of parts to it. I'm going to snip in each part, and then we'll do each part for this this one. Now it says that this is a arithmetic sequence. Arithmetic sequences always have a common difference, also known as the slope. So can you tell me the common difference here? I can give you a formula, but it's the jump. What is the jump to go from one term to the next?
5.
5. So the d equals 5, and that's it for that one.
Okay.
The 10th term. It wants you to find the 10th term. So I think what they're trying to get you to do here is well, that didn't come out right. They're trying to get you to write out a bunch of terms and just find it. Let's hold off and find the 10th term. Let's write the formula for this first, because that's actually more standard. As you would find a rule, or oh, this is odd. Okay, your book does it really odd. This is really weird. You generally just find an explicit rule for the nth term. So the formula is an equals a1 plus n minus 1 times d. Did you see that in class?
Yes, I've seen that.
Okay, so we have the d. Great. Do we have the first term? Yeah, it's minus 4. So we can put this in. Minus 4 plus n minus 1 times 5. This is correct, but not preferred. They would expect you to simplify, so you have to distribute in. An equals minus 4 plus 5n minus 5. So an equals 5n minus 9. So that's the answer to part D.
Okay.
Now, I know we're doing this out of order, but this is generally like, first thing you always do is find the rule, because then when you want to find the 10th term, how do you find the 10th term with this rule?
You can just plug it in.
You just put the number n equals 10 in, and you get a10 equals 5 times 10 minus 9, which is 41.
Okay.
Now, part C, which this one really goes along with part A. Like, you need to know what's happening between terms. Like, how do you go from, and let me snip in the numbers again. I should just copy them. It's like, how do you go from minus 4 to 1? And you just told me this. You add 5, right? You said that. So a2 is equal to a1 plus 5. Would you agree
Yeah.
with that? Okay. A3 is a2 plus 5, because you're just adding 5 to it. So you can write a few of these out until you see a pattern.
An equals an minus 1 plus 5.
Yes, perfect.
Okay, good. Okay, yeah, that makes sense.
All right. Number 25 and number 25. Okay, so okay, 25. We got a geometric sequence this time. So geometric sequences, they always have a common ratio. What is the ratio that that you see here?
1/3.
So that would be true if you're going, it's always the next divided by the previous.
Oh,
So
okay.
that's 6 over 2, which is 3. And if this were like multiple choice, you would see both options there. So you have to be very, very careful.
Yeah.
So that's the thing that it asks for in A. What is the common ratio? Let me snip that in. Okay, so the common ratio R here is equal to that. We're going to do part D next because, again, you kind of generally find the rule for this. So this is another one that you'll have to write. Make sure you know it's A sub n equals A1 R to the n minus 1 power. Does that seem right? Yes.
I mean, I've seen it.
Okay. I think that's right.
Yeah.
So what do you need? Well, you need the first term. Got that. Need R. Got that. So we can write this down. AN equals 2 times 3 to the n minus 1 power. So now this is where, if you had said 1/3, you can always check a few terms here. You can say, well, let me let n equal 1. When n equals 1, you get the first term. You get 2 because this just goes away. But when n equals 2, all of a sudden you're multiplying 2 times 1/3, and you would say, oh, well, that's not right. That's not 6. So maybe it's 3. And then you realize, oh, I'm just multiplying by 3 each time.
Okay, good.
Okay, so this is your explicit rule. You find the rule so that you can do what they ask in part B, the 8th term. So the 8th term here is when n equals 8, so a sub 8 equals 2 times 3 to the 8 minus 1 power. That's 2 times 3 to the 7th power. If you got a calculator with you,
Yeah.
please give that a go. See what you find.
279,936.
Wow. Okay, so that's a big number. The next one is a recursive rule for the nth term. So this is I mean, I've actually haven't seen this in a book in a long time where they've asked you this. This is a good question because it isn't kind of a thing that you would obviously do. But let's look at the numbers again. So you've got 6. 6 is equal to 2 times 3. Okay, and then 18 is equal to 6 times 3. And then 54 is equal to 18 times 3. So notice you're taking the next term. A2 is A1 times 3. A3 is A2 times 3. A4 is A3 times 3. So your AN equals AN minus 1 times 3.
Okay.
Now, is this the same as what I just wrote on the left? Does it produce the same thing does the left and the right produce the same thing?
Yes.
Yes. So it could be that you get one or the other. Okay. 28 here. All right, so part A is the common ratio. What's the common ratio here?
-1.
-1. We're going to do part D next, which is to write the formula. AN equals A1 R times n minus 1. So your first term is -2. Your common ratio is -1 to the n minus 1 power. Just writing out the formula. Once you get R and A1, you just go.
Okay.
And then part B is to find the 8th term. Okay, so this is -2, -1 to the 7th power. -1 to the 7th power is -1. -2 times -1 is 2. You could also figure that out by writing out a bunch of these if you wanted. Part C is to figure out a formula here. So the second term, 2, is equal to the first term if you multiply it by -1. The third term is equal to the second term if you multiply it by -1, and so on. So what you're noticing is that it tends to be the ratio is this way you write it. And we use that here. This was the ratio. And this when we're coming up with that formula for C. So A sub n equals A sub n minus 1 times -1.
Is that like a rule or just like a general thing that happens?
It just works for these. Most of the time they're not. Geometric sequences are always going to be, can be written recursively, but not all arithmetic ones can.
Okay.
Well, no, I take that back. I take that back. I guess they all can be. I guess all arithmetic and geometric sequences can be written recursively. They all can. So I think I mean, I would want to do a few more problems, but I think this is probably a golden rule that works a lot.
Okay.
Can't think of an exception at the moment. Okay, on to the next column. I see question 31 circled.
Yes.
Sometimes these are better because they don't have as many parts. It's just kind of a question. All right, the second and eighth terms of a geometric sequence are 3 and 192. Respectively, find the first term, the common ratio, and explicit rule for the end term. Okay, so they're saying a sub 2 equals 3, and a sub 8 equals 192. That's what you get out of this first sentence.
Okay.
So we're going to write the formula: an equals a1 r to the n minus 1 power, and we're going to do that for each of these. So we're going to first do it when n equals 2. So you get a2 equals a1 r to the 2 minus 1 power. But what is a2? A2 is 3, and this is to the power of 1. So now we're going to do it for n equals 8. So we get a sub 8 equals a sub 1 r to the 8 minus 1 power. So a sub 8 equals a1 r to the 7th power. But a sub 8 is really, it's really 192.
Right.
Okay, so what we've done here is we've taken these two pieces of information and written two equations. How many unknowns do you see in these two equations?
2.
2, and you have two equations, so you should be able to solve them. Now, some instructors teach substitution here. What I recommend is you write the bigger number over the smaller number. So we're just going to take this equation, we're going to move it over here. 3 equals a1 r to the 1, and we're going to divide.
Okay.
Okay, so this is 64 equals a1 divided by a1 goes away, r 7 minus 1, because when you have the same bases, you have to subtract the exponents.
Right.
You get 64 equals r to the 6th, so r equals 2, or negative 2, actually.
Oh, okay.
Actually, this problem, they probably weren't expecting that. Okay, it's probably 2, but it could be negative 2. So, any questions on that part?
No, that actually makes sense. Yeah.
Okay, so now you go back to one equation to the other, just like when you're solving a system. I'm going to go back to this one. 3 equals a1 times r to the power of 1. I'm going to use r equals 2. So a1 equals 3 halves. So to write your equation, you need an equals a1 r to the n minus 1 power. We have both now, 3 halves, 2 to the n minus 1 power. So we should check for n equals 8. So if you got a calculator handy, go ahead and put n equals 8 in and see if you get 192 for n equals 8.
I did.
Great. And if you didn't, you would go back and make a mistake. So have we found the first term? Yes, that's the first thing it asked for. Did we find the common ratio? Yes.
Mm-hmm.
And then an explicit rule for this. If you want bonus points with your instructor, you could point out that this question has an error in it because -2 could be r, and it still works for this.
Oh, yeah, it could.
Well, actually, I take that back. Because if you put in here when it goes to the 7th power, it would give you negative 192. So actually, it does not work. They did check this. I'm sorry. No extra points for finding that. Okay. So
I have just like kind of a random question.
go ahead. Yep.
this isn't in our textbook, but our teacher kind of made a big deal about it in class. She was like, "Now your textbook never has like the first like n equals 0 for the first term." And then there was this whole thing about like, oh, it asks you to find like the 98th term. It could be like the 97th then or something like that. But it was like the difference between like A1 and A0.
Yeah, it's a big deal in a lot of other settings. So like in programming, and I'll address your question. Some languages they index starting at 0 and some index starting at 1. And it's a real issue because if you're going between them, you obviously would want to know that. So what your instructor is saying is like, I could give you a sequence like AN equals 3AN minus 1. I'm sorry, let me not do it that way. Your instructor is trying to say that, well, there is such a thing as an n equals 0. Like you could find that a sub 0 equals 1, and for n equals 1, it could be a1 equals 3. And this is okay, but it's not shown in your book, I think is maybe all the point is of that. But I think most sequences in your book start at 1.
Yeah,
And
all of it, we included like practice problems in our notes that start at 0, but not in the book.
okay. So there's other things you might see in math, like you might see this sigma symbol. It can go from like n equals 1 to 4.
Oh yeah, we just talked about this in
So
class.
if it's x to the n, then the first one here would be like x to the 0 plus x to the 1 plus x squared plus x cubed plus x to the 4th. And that's totally reasonable. Now, I assume your instructor probably gives you something like this. They'll say, oh, are these the same? So when you put n equals 1 in, you get x to the 1 minus 1 power plus n goes to 2, you get 2 minus 1 plus x to the 3 minus 1 plus x to the 4 minus 1 plus x to the 5 minus 1. And so you end up getting the same thing, x to the 0 plus x squared plus x cubed plus x fourth. So you can actually move between them and just get the same thing. These are the same here.
Okay, so if I wanted to, I could just move all the n equals 0
I mean, it
problems.
just could be a question, like maybe the instructor asks it that way. Now, do you know how to define an odd, how to define something that's always produces an even number, and then how to produce something that always produces an odd number?
I do not.
Okay, so this is something you want to know. 2n always produces an even number. Okay, so
Okay.
like if n is 1, you get 2. If n is 2, you get 4. If n is 3, you get 6. Like you follow that, right?
Yeah, because like
Okay.
an even times even equals an even, and odd times an odd equals an even too.
So 2n minus 1 or 2n plus 1 give you odd. But if you want to get 1, if you want to get a 1 for this first one, that's no big deal. So let's just say an equals 2n minus 1. When n is 1, you get 1. But what about the second one? If an equals 2n plus 1 and a1 equals, you end up getting 5 to start out. So that's no good, right?
Yeah.
Well, what if n started at, what if you could have n start at, instead of 1, instead of this, what if you had n start at minus 1? Or n start at 0?
Oh.
Okay, and that's, I think, what maybe some of your instructor is trying to emphasize here. Like, so a0 equals 2 times 0 plus 1, which is 1.
Right.
I'm sorry, I put the wrong number here. That should be 3. And that could be something that you could see here. So there's 2 ways to define odds, and you need to know about both of them. But there's only one way to define even functions.
Okay. That makes sense.
All right. So let me just go back a little bit. At some point, your instructor should tell you that there are 3 types of sequences. There's arithmetic. Oh, there's more than that. There's geometric. And then within each of these, you can get recursive or not, recursive or not. But these tend to always work out. But then you can also just get purely recursive sequences, and
Oh.
then you can get like others altogether. I don't know how much you spent over here, but most of your class is over here in this world, because the next thing you're going to do is you're going to find the sum of these.
Oh, we just did that. Like we just did like the sum of
Okay,
sequences.
so let's start. Let's say you're given a sequence, okay, and let's go down the path of, let's say it's arithmetic. So here's what you can do. You can write the formula for it. You can write an explicit formula for it. We did that a bunch today.
Yeah.
You can find a sum, but it has to be it's called a it's a finite number of terms. Okay, like you can't find it. You cannot find an infinite sum of arithmetic, but you can find like the sum of the first 10 terms, the first 100 terms. Okay. So if you're trying to do what's called an infinite sum, this does not exist. Okay. But if
Okay.
you go down this path of, oh, I got a geometric sequence, well, what can you do with that? Well, you can write the formula, explicit formula. Here, though, you actually can find a partial sum, meaning like finite. And then in some cases, you can find an infinite sum. This is okay in some cases.
We were doing this thing and she was like, "Oh, but I have to define n as infinity and then I can find the infinite sum." That like she said something like that.
Yes. Yes. So for example, here, like this may, let's say an equals 1 over n. No, let me do it this. Let me do it differently. Let's say I give you a sequence. I tell you that it's 1, 1/2, 1/4, 1/8, and so on. Okay, this is a geometric sequence. What is the value of r here?
It like
It's the next term divided by the previous term.
okay.
And sometimes if you get a really kind of difficult instructor, they actually might make the first few work out, not the other ones. So sometimes you have to try more than these, but you end up getting 1/2 for r.
Yeah.
Okay, so this is now, okay, so can we write a formula for this? Yes, it's a1 r to the n minus 1 power. So it's 1 times 1/2 to the n minus 1 power, which is just 1/2 to the n minus 1 power. That's your formula for this. So you can always write the formula. Now I could ask you for the sum. I could ask you for the sum of this. I could say, what's the sum of the first 4 terms? Okay. Now for the first 4 terms, you might just say, well, I'll just write them and add them. That's totally reasonable, and you get whatever you get. There's also a formula for a partial sum, which I will be looking. The infinite sum formula is much more simple. Partial sum of geometric series. Okay, so your partial sum, so your sum of like n terms is a1, 1 minus r to the n over 1 minus r. So let's say I wanted the sum of the first 4 terms. It would be the first term, 1 minus the ratio, which is 1/2, n is 4,
Oh, because it's a number of terms. Okay.
over 1 minus 1/2. So whatever this is, it should be the same as this.
Okay.
And you will probably get some problems like this. Now, believe it or not, you can find the infinite sum of what I just gave you, because the value of r is less than 1. If the ratio, the absolute value of the common ratio is less than 1, which it is in this case, it's 1/2. That was what we found up here. If the absolute value of that number is less than 1, the infinite sum is the first term over 1 minus r. So it'd be 1 over 1 minus 1/2, which equals 2.
Oh, yeah, no, she has that in her notes, the, like, absolute value of R is less than 1.
Yeah. So now you might think, well, so let's just go back to the sequence I just gave you. I'll make it slightly different. 2, -1, +1/2, -1/4, +1/8, and so on. Okay, so the first term is 2. The ratio between terms is -1/2. -1/2 first, or next one divided by the previous. And it works for this one over here. Like if you're like, well, I don't know if I believe you, so let's do the next one. 1/2 over -1. It's still that. Well, let's look at one more. It's always going to be that. Is that okay?
Yeah, that makes sense.
Okay, so now let's say I wanted the sum of the first 9 terms. Okay, I got to use that formula. I got to find it's a1 1 minus r to the 9 over 1 minus r. So your first term is 2, 1 minus -1/2 to the 9th power over 1 minus a -1/2. Now you could also just write them all out and add them up, but usually an instructor would give you more than you could for that. But now you could definitely find an infinite sum. It's a1 over 1 minus r if the absolute value of r is less than 1. Your r is -1/2. The absolute value of -1/2 is 1/2, and that is less than 1. So you're okay there. Your first term in what I just described is 2. I just made that up, but it's 2 over 1 minus -1/2. So this is 2 over 3/2, and this reduces into 4/3. Believe it or not, this thing becomes 4/3.
Oh, wow.
Yeah.
That's so odd.
Yes, it is. There's kind of workarounds though. Like let's say you didn't know this formula, you were stuck on a test. You can sort of like sum up a bunch of terms, like 100 or 1,000 or however many your calculator can do before it gets tired, runs out of memory, and you'll get something really close to this. You'll say, well, it kind of looks like 4/3, or you can just learn the formula.
Wow. Okay.
All right. Well, I think this is a great place for us to stop. I'll send out the notes in the screen recording shortly. Thanks again for scheduling, and I'll see you next time.
Thank you so much.
You're welcome. Have a great night.
Thank you. Bye.